In this video, we're going to spend more time looking at chair structures and kind of dissecting them and finding out why they're useful, and then hopefully getting more comfortable drawing them. So what I want to do is recap what chair structures are. So chair structures, there's a few ways to kind of think about them. So we will, number one, they're bond line structures of cyclohexane. And you can add other atoms in them or around them. There are more interesting chair structures out there than cyclohexane, but it's a good starting place. So if you recall, cyclohexane is this hexagon shape. We have 6 carbons in a ring. And so the regular shape that we would think to draw would be a hexagon. And that's useful for some molecules, particularly those with a lot of double bonds, and then become overall flat because most of the carbons are sp2 hybridized. But what we want to do is consider a 3-dimensional component when all of the carbons are tetrahedral. And so what that looks like is this chair structure. So I've just drawn one version. I could have drawn the other version. Hopefully you're getting fast at drawing these things because we'll draw a few of them. So, and a few is maybe an understatement. Okay, so I show the dots for the various corners. There's 6 of them because there are 6 atoms in this ring that's depicted as one of these 2 chair structures. Another way to think about it is it's sort of a tilted front view. So in addition to just being a simple bond line depiction of cyclohexane, it's sort of a 3-dimensional front view of cyclohexane. Okay, so what I mean by that is, well, if we look at the hexagon again, this is the top view of our molecule. And what we're going to do is sort of tilt or rotate. And then the chair structure, oh, I just got off to a bad start there. The chair structure would be sort of the front view. And so maybe another way of looking at it is if I told you that these bonds matched each other. Okay, that's a little bit of it's harder sometimes to make that connection right away. In fact, maybe there's even another way I could try to explain this. It might still be a bit confusing, and that's okay. Keep pushing forward and plowing ahead and drawing chair structures. These ways of thinking about it aren't the most important thing. It's your ability to add groups or substituents to the chair structure that's important. Regardless, let's go ahead and talk about it at least. So if we had to draw wedges and dashes, we usually should not, I should emphasize, I feel bad taking points off on exams when people do add wedges and dashes because they don't do it in the right places. But if we had to, the places we could get away with are within the ring itself. So I have a bigger chair structure here. And so if I had to add wedges, what I would do is I would add a wedge to the sort of lower 3 bonds, the lower 3 bonds, okay? These bonds are coming out at us. These are in front, coming out towards us. Okay, now the other ones is going to look a little awkward. If we add wedges, we should add dashes. And for every wedge, there truly is a dash. So I have 3 dashed bonds that are more raised or kind of higher up, but in reality, they're directly behind the wedge carbons, but we've just tilted it so that we can see the molecule. Remember, this is truly a sort of tilted front view of a hexagon. Okay, so these are in back. And that's always the case. The 3 bonds that are raised or higher in our chair structure are always in the back, and the 3 bonds that are lower are always in the front. And then what we do is we could block out two of the atoms. The starred atoms are in plane with paper. So they're sort of they sort of designate the boundary between going forward and going back. So it's the two cornered carbons. And I always like to start with those cornered carbons when I'm doing a deeper analysis. So what does this mean? Well, it means that these two carbons are in front and these two carbons are in back. And I already mentioned that the sort of flapped carbons, I guess, the two carbons on the end, those are in plane with the paper. Okay, so we usually don't want to add wedges and dashes. If we have to, we put them actually within the six-membered ring, not on the groups attached to the six-membered ring. So what does it look like when we attach groups to the six-membered ring? We're going to introduce a few new terms. So before we do, let's draw at least two of the groups. So adding substituents, and remember substituents are our groups. So adding substituents to a chair structure. What I want to do is first draw, and what I'll do for a while is draw the flat hexagon. And I'll just pick maybe this carbon to add groups A and B. Okay, and maybe I'll even put a dot there. All right, so what I can do is convert this into a chair structure. And I will pick this version of the chair structure. It's the one that we've been drawing. And then from there, I need to add groups. And I always, whenever I'm starting to add groups, you'll see as we get into this that the easiest places to add groups are on the farthest left or farthest right side. We get to pick anywhere we want to add groups A and B. I know it looks like, well, this is on, excuse me, let me get a highlighter out. It looks like that position is furthest to the right, and this position is clearly furthest to the right, and they match. That is totally coincidental. Whatever I choose this carbon over here to be, I can pick anywhere I want on the ring to add those substituents. But regardless, we'll stick to this for now. We don't need to confuse that point until later in the game. When I add groups, I can only add groups to one of these two positions, okay? Directly straight down and then up and to the right. What I want to point out about these two positions is that one of them is parallel to lines that are 2 bonds away, and that'll be important later. I mean, it's important right away, I guess, but that will be emphasized later. So what we do is we add groups, and we could add either A and B to the slanted line and the straight line. So we've added 2 substituents in every position on the carbon. Okay, I'm not going to keep those dots. Every position on the carbon can have only 2 positions added. Sometimes they'll be pointed directly up, sometimes directly down, sometimes diagonally up and to the right, down and to the left, whatever. Okay, they can be in various positions. So we've just added 2 groups. So number 1, we recognize when we're adding substituents that each carbon can have only 2 groups. Where substituents are our groups. Substituents just means something that has substituted for hydrogen. Okay, the other thing to consider is the groups can be either, and these are important buzzwords for us, they can be either axial or equatorial. Axial or equatorial. Axial, these point straight up or down. Point straight upwards or straight downwards. Equatorial point diagonally. They point diagonally. It could be up and to the left, down to the right, whatever. In various directions, we'll see that. But they point diagonally, they're slanted. And if you kind of squint, they're more horizontal, which is where this equator comes into the name. Equatorial means equator-like, okay? So somewhat, they're more so horizontal than the axial substituents. So one of the most misspelled words by organic chemistry students and faculty probably is the word equatorial. They like to put equatorial with an I. Anyway, it's equatorial. And I mention that not because I care how well you can spell this word right now. It'd be great if it's always great when we spell correctly, but you know, I've made mistakes in these videos. But it's just to remind you that the equatorial positions are more horizontal, or they have this kind of slanted dynamic to them, whereas the axial are always kind of straight up, or as we'll see, straight down. So what we need to recognize is that there are 6 atoms in our ring, and we need to be able to draw 2 substituents, and 1 axial and 1 equatorial per carbon. So each carbon has 1 equatorial and 1 axial group. Now the big kind of test comes in, we need to be able to draw the groups attached at any position. That's a big goal for us. That's going to be a tall order. And honestly, our ability to do that quickly as possible, as early as possible in this module will be the key to our success on a large part of exam 3, as chair structures will cover in a big part of it. Okay. So, and that's kind of point 3 as I'm thinking about substituents. So I'm going to draw a number 3 here. Okay. So now point 4 has to do with the 2 versions of the chair structures. That is, when I flip, quote, a chair, when I flip a chair, all axial and equatorial groups flip. All axial and equatorial groups flip. Okay, so when I flip the chair, all the groups flip. So what does that mean? Well, if I consider my chair structure from before, we have A and B. Okay, so now we can actually label these things. A is my equatorial position. B is my axial position. Do you see why? Well, B is axial because it's going straight down. Axial positions are either straight up or straight down. They're kind of aligned with some sort of axis out there. Equatorial, like the equator, is more horizontal. It's slanted, so it's not perfectly straight out. And the reason why it's not perfectly right or left, which would make life so much easier, I realize, is because that's not accurate. These, remember, chair structures are actually fairly accurate depictions of the 3-dimensional nature of 6-membered rings. So we're going to try to capture the angles that they go. So up and to the right is where the group, the equatorial position, would be on the carbon that I've just labeled with a dot. Okay, so what we have here is a chair structure, a chair version. And what I'm going to do is I'm going to kind of do a conformational free rotation, and we'll look at the actual free rotation movements in future in upcoming lectures. But what's going to happen here is the simultaneous movement of all of the bonds within the ring to get us to something like this. Now, the substituent bonds do not rotate. They just kind of go along for the ride, but let's not consider them actually doing free rotation. What I do know is that the furthest right carbon, which I've labeled with a dot and I'll emphasize with a highlighter, remains the furthest right carbon after my free rotation event. And we call this free rotation event a chair flip. Again, we'll look at a lot more details on this in future lectures. Don't worry if you're not following the chair flip. What I do want you to follow is just observe the point that at this position, now the equatorial and the axial groups are aligned in this way, as I've drawn, where the axial position is pointing straight up and the equatorial position is pointing straight down. Now, A was a little bit higher than B in the original structure, and it's going to stay that way. It's just that now, after the chair flip, A has flipped to axial, B has flipped to equatorial. So again, I'm doing a lot in this point, but all I want to do is just start the conversation about the chair flipping of conformational isomers, where the chairs not only flip into a separate version, but the equatorial and the axial positions also flip. Okay, so what I want to do now is draw the groups that I was alluding to, that is the axial and the equatorial positions. So we'll start with the axial groups. And perhaps, looking at the time, maybe this makes sense to put in a separate movie. So we'll just capture drawing the equatorial and the axial groups in another movie. So I'm going to stop this one. We looked at more details of chair structures. We saw more, we kind of thought more deeply about chair structures, looked at what happens when we rotate them and that sort of thing. So I guess this served as sort of a backup introduction.